Hello. In this tutorial, I'll be showing you how to use a few of the other coding tools to calculate additional things using previously determined outcomes of the PyUserCalc melting model. These are mostly focused on U-series isotope results and incorporate radioactive decay, but there's also a stable element concentration tool I'll show you. While all three of these calculators are relatively new, at least newer than the original UserCalc melting code, and they haven't been incorporated into the UserCalc or StableCalc classes or driver scripts, these two Python files down here. And this means they have a lot of inline code within the Jupyter notebooks. They are fully functioning and have been tested against expected outcomes, so we think they're calculating correctly. If you run UserCalc melting calculations using any of the transport models, and you determined them using a relatively recent version of the UserCalc Jupyter notebook, either PyUserCalc, in my case, version 3.3 is the most recent, but if you're looking at this video later, there might have been even more recent versions, or StableCalc, which at the moment for me is version 1.0. Those notebooks are set up to set up file folders using the user-defined run name, which was also the input file name, and then by timestamps so that the runs did not overwrite each other. So for instance, if I use the sample input file, if I look at my data folder, I have many input files, but here's sample.csv. And then if I go to my outputs under sample, I have run this dozens of times, all with different timestamps, and that's because I use it for testing when I'm developing new code, so it's been run over and over again. These are automatically saved in year, month, day, hour, minute, second format. The first thing the scripts I'm going to show you do is retrieve prior results to do your follow-up calculations. That means you just need to know the run name, like sample, and the timestamp that you want to work on. So I'm going to focus on this one, and I'm actually going to copy that file name so that it's easy for me to enter. I recommend copying them somewhere. You can even write them down in a file, so it's easy to enter them when you're running the code. Okay, so the tools in question are first a radioactive decay calculator called U-series Decay that simulates simple decay since magma formation. There's also a two-dimensional integration tool that integrates over the length of the melting column, simulating triangular melting regimes, and there's also one for stable elements, but of course that one has no radioactive decay to worry about, and so the formulas are a bit simpler. I'll tackle these, what they do, and how to use them one at a time. So first I'm going to open the U-series Decay calculator, which looks like this. The decay calculator is relatively simple. It can either be used to calculate a modified melt composition for a simple amount of time that has elapsed since eruption, or while pooling in a crustal magma chamber. Either way, it's simply an imposed period of time. You tell the code the number of years that have passed, and it calculates the decay outcomes. So you give it a time interval, like 4,000 years, and it calculates a modified melt composition and saves those results as new output files to a new output folder. They're nested within the same timestamp folder under the additional calculations folder. That way they also won't overwrite each other or anything else you've done. The other thing this script can do is calculate the effects of radioactive decay as magma actually migrates through a lithospheric layer of set thickness. This is still just setting a time interval using a transport rate and thickness as distance traveled. But there are two differences. The first is that you set the transport rate instead of the time, so the input is just a little different. The other difference is that you can generate a modified output results file that imposes decay at the top of the melt column, even if you previously calculated melting to shallower depths. So for example, say you ran a UserCalc set of modeling calculations all the way to 2 kilobars, and that was your pressure, your final pressure. But you now want to see what happens if melting actually stopped at 5 kilobars and then it took a certain amount of time to travel through that 5 kilobar layer and undergo decay. You can create a modified output column that takes the values at 5 kilobars and decays them the rest of the way to 0 kilobars, all the way to the surface, with simple travel and decay for that whole top layer, and it creates a new output column. So I'm going to walk you through one quick calculation and how it's set up for a sample file run and a particular timestamp. And I'll show you where it saves and what it produces. So this one will ask me questions. I just need to be ready to answer them. So sample is the name of the input file, and then I have copied this value from that folder. I enter that. Then it's going to create any new folders that are necessary in the correct locations so that I can find them later. And it will ask me one follow-up question. Was the prior model run a standard 1D column calculation or, say, a 2D integration result that you're now going to impose aging on? Say it was a two-dimensional integrated value and you now want to simulate what happens if it erupts and sits on the seafloor or at a volcano for 1,000 years. So this was a one-dimensional normal run, not the result of a two-dimensional calculation. So I'm just going to write 1. All of these tools are modular in this way, so there are some back and forth questions that allow you to do some recalculations like this in all of these tools. So now it's going to ask me what types of calculations were run. Did I run it? And which ones do I want to actually use here? It's possible I don't care about some of them. So did I run an equilibrium, transport model, disequilibrium, and a scaled one? And if so, what was the Damkohler number? The only reason it's asking these questions is so it knows what output files to receive and what they were named. So yes, yes, and yes, and the Damkohler number was 0.1. Now it's going to try to find those data sets. This is where you might get an error if I typed something wrong above and the files can't be found. And then here in the next cell, I tell it what I want to do for my input or my conditions. So how much storage time should pass, say 1,000 years or 10,000 years. If it's simple storage and decay, you can give this a lithospheric layer and calculate a value. So this is, for example, if I want to simulate magma that has risen to a certain depth and then it sits there and decays. If it's at the surface, this should be 0 for eruptions. Alternately, I can put in inputs for a lithospheric pressure depth, in this case 5 kilobars, and a conversion for pressure. I don't need to change this one. I'm happy with the coefficient being used. And then I want to know a transport rate. So this would be 1,500 centimeters per year, and I can put in any number in centimeters per year and it will do all the unit conversions for me. I don't touch this cell, it just defines the transport time required for this scenario. I also do have decay constants in here. Those don't usually need to be updated, but if you want to use slightly newer values, you can. And then the rest of these values that I've entered are all saved and saved to a run log, so I know what I did if I want to look back later and try something different. The cell below gives me the input tables so I can make sure they look correct. They take many lines if you expand them fully. And they all look like they've been retrieved correctly. Now, I'm going to tell it what my partition coefficient values were, and it's going to go to the input file and find them. And this is because the output files don't have the partition coefficients, but they are needed to get solid versus liquid concentrations out of the results. So this is simply retrieving information from my original input file for this run, based on the run name I gave it of sample. I also need to tell it what the initial activity values were, because it won't necessarily know this. That's also important for getting my initial concentrations. And then the next cell extracts the values from the prior runs. Now, if I'm going to calculate transport calculations over time, the next cell is necessary to actually retrieve and set up the spreadsheet. So it's possible you truncated melting, for example, at 5 kilobars in your calculations using PyUserCalc, but you now want to calculate values all the way up to 0 using Decay. So you need to add those rows. This simply adds additional rows to your CSV file as a data frame so that you can fill them with new values later. This is a warning about some of the methods. It's currently working. We may need to update this, but this is just an alert. It's not saying that anything went wrong. So the next question asks me if I'm calculating isotopic decay during transport through the lithosphere. I'm going to say yes, as opposed to a fixed time interval after eruption or in a magma chamber. I'm then going to run the next cell, which retrieves the information necessary and implements my decisions and saves them to the run log, and then finish implementing those decisions. All of the yeses and nos, now it knows which values to retrieve and use from above. These are the Zhao formulation for U-series decay equations. They're standard U-series decay equations, and this is what the next few cells will be doing. Because all the code is inline in these notebooks, it makes the cells fairly long to have all of these formulas, and so that's kind of the one drawback to the fact that we haven't moved any of this to a separate class. It just looks like a lot, but if you don't edit these cells, they should run just fine. So the next 3 cells will actually extract the final melting concentrations using the above retrieved values, and then does it for equilibrium, disequilibrium, and scaled disequilibrium. And you can actually see them printed to the screen to make sure they look correct. So we have all of our extracted values, and then the next one saves results to directories. And the last thing you can do is you can actually also do this for batch results. However, batch operations from PyUserCalc only save final melting calculations, not full 1D columns saved at every step. So all this will do is calculate the effects of decay on the final results and generate a new set of batch values that you can plot to figures. You do need to tell it what phi and W values, the porosities and upwelling rates you used before, so that the figures will have the correct legends and so that your data tables will have the correct labels. It builds data tables and then runs all of these calculations and produces concentrations and activity ratios for each of the 3 models. And then finally, we're going to import our plotting figures from UserCalc and see what we have. So these are now modified, and it prints the decay interval that was calculated for the lithospheric thickness and transport rate that I gave it. And it retrieved all of these results, but these numbers were inputted above again so that it knew how to print them. And that is this entire notebook and what it does. Now, the 2-dimensional calculator is set up similarly. Like I said, they're modular, so you can go back and forth and retrieve information from the other tools. So for now, for example, I could use what I just did in the U-series decay calculator tool, and I could now integrate that over depth all the way to the surface with a pressure of 0 at the end. There's some simple explanation and summary of what this tool does, but just like before, if I'm going to run it, I'll want this information here, and then I need to give it a run name and timestamp. just like before, and I'm going to use the same one. Again, it's going to create new directories where needed. Now this time, I may want to actually determine the integrated result from my previous calculation. And so what I'm doing is looking up that timestamp. So it's within my additional calculations folder, and this is the one I have just started. It doesn't have anything, but the one I ran a few minutes ago is right here. It has its own run log, and if I go into the results, it has all this other information. So this timestamp I can actually use. So I'm going to copy that one. And when I run this, it will ask me, has the prior model result been revised to consider lithospheric transport and decay? And I'm going to say yes. If I look at my results, they used 1029.0. And I believe I need to type the 0.0, because the reason to type this in is so it finds the correct files. And here's the timestamp that I copied. And hopefully I entered all of that correctly. If not, we'll do it again. And like before, I ran all of these, and I would like to see what happens to all of them when I integrate them. And so I enter all of those values as yes and my dam caller number, so it can find all the correct outputs and retrieve them and then use them in my new calculations. So now I'm going to retrieve all of that. This is where, again, some of these cells might spit out errors. Aha! I cannot find the file or the directory, so I must have entered a value slightly incorrectly. Let me see what that should look like. And it turned out that these do not append, this is the 0.0 value that is added to the figures. This is something I can probably edit in a future version, so it's not confusing. But the other thing I could have done is simply copy this number to make sure I did it correctly when entering it. But now my values have all been correctly entered without any error messages. And the error messages are helpful for indicating that you need to fix something. So now I have entered my values, I can display them on the screen, and they all look correct and all looks happy. Now in the next cell, I'm going to set up the two-dimensional integration to make sure that it runs properly and the way that I want. And one thing that I need to do when calculating integration over a triangular melting regime for uranium series is consider how long it takes for the magma that has separated from any individual path along that triangle to how much time it takes for it to get to the ridge axis where it pools and aggregates. Unlike stable element calculations for two-dimensional integration, that travel time for the segregated magma or partial melt is really important, and it needs to consider the path length as well as the transport rate. The path length part is built in to the script, but you need to give it a lithospheric transport rate. However, this tends to be relatively poorly constrained. You also can give it a theta value, which is the corner angle on your triangular melting regime. The default is 45 degrees. Changing this simply changes the path length for those aggregated melts. Because the lithospheric transport rate is relatively poorly constrained in most circumstances, the model is set up to try a variety of values over a range of lithospheric transport rates. You can either put this in manually as a series of values like 10, 100, and 1,000 centimeters a year, or you can create an array using the log space NumPy expression, which is what I've done here. And then the rest of this, other than putting in a theta value and confirming that you are using a final pressure value of 0, which is just for bookkeeping in your output tables, all All the rest of the things you need to do are similar to the decay calculator. You need to give it initial values because the script would not know those. And then the rest of this is confirming decay constants and putting everything in a run log. So I'm going to implement all of those. And just like before, I need to retrieve partition coefficients for my concentration calculations. Then I'm going to run the Zhao formulas for determining decay during transport. And I'm also going to integrate over the entire depth of the melting column. So this is just retrieving and calculating initial concentrations. And then this cell determines the results for equilibrium melting, and then disequilibrium, and then scale disequilibrium with a Kohler number. All of these do spit out a snippet of column result, or actually all of the results for each of the different lithospheric transport rates, so that you get the final integrated values as masses, which is what's being integrated, and then the calculated activity ratios. And then all of that is saved. The final tool I can show you is the stable element integration tool, which is much simpler. This one only needs to consider the entire melting column for each element of interest. And so for example, I have this one already set up to use values from a prior run for the sample stable model that was tested excuse me, in the stable calc notebook. So I've already entered a run name and a stamp instead of letting it ask me questions. I'm going to create my directories. I'm going to confirm all of the models I'm running, equilibrium, disequilibrium, scaled disequilibrium, and a Kohler number for that one, and implement those. And then I'm going to import the data sets. Now, these data sets already have concentrations and degrees of melting in them, not activities or log concentration values. And so I don't need anything else for this notebook. I just need to calculate these values. So I generate my data frames, and then I'm going to display the input tables to make sure they look correct. Find the elements. This is a different step from before. They're going to be extracted from the input file that lists and the output results from the prior calculation using the labels on the headers from those data tables. And here's the list. I can confirm it looks correct. Then I'm going to build some data frames that I will fill with my results, determine mass with depth, and then integrate over those masses. And then I'm going to see my outputs. Now it's a single row because these are simple integrated values. So that's my equilibrium result, my disequilibrium result, and now my scaled disequilibrium result. And then all of that can be exported to a series of data tables, which can be found. This is from the U-series results, but you can export all of these as data tables with CSVs.